Introduction to RSA-PSS. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with a focus on networking. Also, hit the bell icon to get notified of new videos. Today we're diving into RSA-PSS, which stands for RSA Probabilistic Signature Scheme. This is one of the most important and secure digital signature schemes available today. Unlike the older PKCS No. 1 version 1.5 signature scheme, RSA-PSS introduces randomness into the signature generation process, which provides provable security properties. This randomness means that signing the same message multiple times will produce different signatures each time, making it much more resistant to various cryptographic attacks. The scheme was standardized in PKCS No. 1, version 2.1, which is documented in RFC 8017. This RFC is the authoritative specification for RSA cryptography, replacing the older RFC 3447. RSA-PSS has been adopted by major standards bodies and is recommended by cryptographic experts because of its strong security guarantees. The scheme is based on the mask generation function, specifically MGF1, which we will explore in detail throughout this presentation. What makes RSA-PSS particularly important is that it has a security proof in the random oracle model. This means that cryptographers have mathematically proven that if RSA itself is secure, then RSA-PSS is also secure under specific assumptions. This level of assurance is not available for older signature schemes like the deterministic PKCS version 1.5 scheme, which has known theoretical weaknesses even though practical attacks remain difficult. RSA-PSS versus traditional RSA signatures. To understand why RSA-PSS is so important, we need to compare it with the traditional RSA signature scheme known as PKCS No. 1 version 1.5. The traditional scheme is deterministic, meaning that if you sign the same message with the same key, you will always get exactly the same signature. While this might seem reasonable at first, it introduces subtle security vulnerabilities that cryptographers have identified over the years. The deterministic nature of traditional RSA signatures makes them vulnerable to various theoretical attacks. One issue is that an attacker who sees many signatures can potentially learn information about the relationship between messages and their signatures. Another problem is that the padding scheme used in PKCS 1.5, while functional, was not designed with a security proof. It was created based on engineering judgment rather than rigorous mathematical analysis. RSA-PSS addresses these concerns by introducing randomness through a salt value. Every time you sign a message, a new random salt is generated. This salt is incorporated into the signature computation in a way that makes each signature unique, even for the same message. The randomness does not prevent signature verification. Anyone with the public key can still verify that a signature is valid. But it does prevent an attacker from learning patterns or exploiting the deterministic nature of the signing process. The security proof for RSA-PSS shows that breaking the scheme is as hard as solving the RSA problem itself, assuming the hash function and mask generation function behave like random oracles. This is a much stronger security guarantee than what we have for traditional RSA signatures. Modern security standards and frameworks increasingly require or recommend RSA-PSS over the older scheme because of these proven security properties. Core components of RSA-PSS. Let's break down the essential building blocks that make RSA-PSS work. At the foundation, we have the RSA key pair, which consists of a private key used for signing and a public key used for verification. The private key includes the modulus n and the private exponent d, while the public key contains the modulus n and the public exponent d. These are the same RSA keys used in other RSA-based cryptographic operations. The next critical component is the hash function. RSA-PSS relies heavily on cryptographic hash functions, for example, SHA-256, SHA-384, or SHA-512. The hash function is used in multiple places throughout the signature generation process. First, it is used to hash the message itself, creating a fixed-size digest regardless of the message length. Then it is used within the mask generation function to create the masks that provide the randomness and security properties of the scheme. The mask generation function, specifically MGF1, is perhaps the most unique aspect of RSA-PSS. MGF1 takes an input seed and generates an arbitrary length output that appears random. It does this by repeatedly hashing the seed with an incrementing counter, then concatenating the hash outputs until you have enough bytes. This function is deterministic. Given the same seed, it always produces the same output, but the output appears completely random and unpredictable without knowing the seed. Finally, we have the salt, which is a random value generated fresh for each signature. The salt length is typically chosen to match the hash function output length, so for SHA-256 you would use a 32-byte salt. This salt is the source of randomness that makes each signature unique. It is incorporated into the signature in a way that allows verifiers to reconstruct it during verification, so you do not need to transmit the salt separately from the signature. Message encoding in RSA-PSS. The message encoding process in RSA-PSS is where all the cryptographic components come together. This process transforms your original message and a random salt into an encoded message that can then be signed using the RSA private key. Understanding this encoding is crucial because it's where the security properties of PSS are implemented. The process begins by hashing your message with the chosen hash function. Let's say SHA-256. This gives you a 32-byte message hash, which we will call M-hash. Next, we generate a random salt of the same length, another 32 bytes. These two values, along with an 8-byte padding field of zeros, are concatenated together to form M'. So, M' consists of 8 0 bytes, followed by the 32-byte M-hash, followed by the 32-byte salt, for a total of 72 bytes. We then hash M' to get another hash value called H. This H value becomes the core of our encoded message. Now comes the interesting part with the mask generation function. We use MGF1 with H as the seed to generate a mask that is as long as we need it to be. This mask will be XO-red with a data block to obscure it. The data block that gets masked consists of padding bytes followed by a byte representing the salt length, followed by the actual salt. The padding is typically all zeros except for 1 byte. The length of this data block is calculated to ensure that the final encoded message fits within the RSA modulus size. After XO-ring the data block with the mask, we get what is called the masked database. The final encoded message is assembled by concatenating masked DB, then H, and finally a trailer byte that indicates which hash function was used. This entire structure is then treated as a big integer and processed with the RSA signing operation using the private key exponent. The beauty of this construction is that it incorporates randomness throughout while still being deterministically verifiable. The mask generation function MGF1. MGF1 deserves special attention because it is the cryptographic primitive that provides the masking capability in RSA-PSS. The mask generation function is defined in the same RFC 8017 that defines RSA-PSS itself, and it is specifically designed to generate a pseudorandom bit string of any desired length from a seed value. The way MGF1 works is elegantly simple. You provide it with two inputs: a seed, which is typically a hash value, and a length parameter indicating how many bytes of output you need. MGF1 then enters a loop where it hashes the seed concatenated with a 4-byte counter. The counter starts at 0 and increments on each iteration. Each iteration produces one hash output. Let me make this concrete with an example. Suppose we are using SHA-256 as the hash function, which produces 32-byte outputs. If we need 64 bytes of mask output, MGF1 will run the hash twice. The first iteration hashes the seed concatenated with the 4-byte value representing 0, giving us the first 32 bytes. The second iteration hashes the seed concatenated with the 4-byte value representing 1, giving us another 32 bytes. These are concatenated to give our 64-byte mask. If the desired length is not a perfect multiple of the hash output length, MGF1 simply truncates the final hash output to get the exact number of bytes needed. For example, if we needed 50 bytes of output with RSA-256, we would do 2 hash iterations to get 64 bytes, then take only the first 50 bytes of that result. The security of MGF1 relies on the properties of the underlying hash function. Because hash functions are designed to be one-way and to produce outputs that appear random, the output of MGF1 also appears random and unpredictable unless you know the seed. This makes it perfect for creating the masks that obscure the salt and other data in the RSA-PSS encoding process. RSA-PSS Signature Generation Process. Now let's walk through the complete signature generation process step by step, seeing how all the components we've discussed come together. This process takes your message and produces a signature that proves you possess the private key and that the signature is bound to this specific message. Step 1 is message hashing. You take your message, which could be any length, and hash it using your chosen hash function. If you're using RSA-256, this gives you a 32-byte hash value called mhash. This step ensures that regardless of whether your message is 10 bytes or 10 gigabytes, you're working with a fixed size value in the subsequent steps. Step 2 is salt generation. You use a cryptographically secure random number generator to create a salt value. The salt length typically matches your hash output length, so for RSA-256 you would generate 32 random bytes. This randomness is critical. If you reuse salts or use predictable salts, you lose the security benefits of PSS. Each signature should use a completely fresh, unpredictable salt. Step 3 is forming M'. You concatenate 8 0 bytes, your 32-byte mhash, and your 32-byte salt. These 8 0 bytes might seem arbitrary, but they are part of the PSS specification and serve as padding. The resulting 72-byte value is M', which you then hash again to get H. This double hashing with the salt is what binds the salt to the message in a way that makes the signature verifiable. Step 4 involves the mask generation function. You use MGF1 with H as the seed to generate a mask. The length of this mask depends on your RSA key size and hash length, but it needs to be long enough to cover the data block you are about to mask. For example, with a 2048-bit RSA key and RSA-256, you might generate a mask that is about 220 bytes long. Step 5 involves creating and masking the data block. You construct a data block consisting of padding zeros, a single byte indicating the hash algorithm, and the salt. You then XOR this data block with the mask you generated, which creates a masked DB. This masking operation obscures the salt while still allowing it to be recovered during verification. Step 6 is assembling the encoded message. You concatenate masked DB, H, and a trailer byte. The trailer byte is typically hex BC and indicates the end of the encoded message. This complete encoded message is then converted to an integer. Finally, step 7 is the RSA signature operation itself. You take the encoded message as an integer and raise it to the power of d, the private exponent, modulo n, the RSA modulus. This gives you the signature value S. This signature, when encoded as bytes, is what you transmit along with your message. RSA-PSS Signature Verification Process. Verification is the inverse of the signing process, where someone with the public key can check whether a signature is valid for a given message. The verification process reconstructs the encoded message from the signature, checking that it has the correct structure and that the salt properly binds the signature to the message. The first step in verification is the RSA verification operation. The verifier takes the signature value S and raises it to the power of E, the public exponent, modulo n, the RSA modulus. Since s equals m to the power of d mod n, and we are computing s to the power of e mod n, this gives us back m because d and e are inverses modulo phi of n. So, we recover the encoded message. Next, the verifier separates this encoded message into its components. The rightmost byte should be the trailer byte, typically hex BC. The next bytes from the right are h, the hash value that was used as the MGF1 seed. The remaining bytes on the left are masked dB, the masked data block. The verifier knows the lengths of each of these components based on the hash function and RSA key size. The third step is unmasking the data block. The verifier uses MGF1 with the recovered H value as the seed to regenerate the same mask that was used during signing. The verifier then XORs masked dB with this regenerated mask to recover the original data block. This data block contains padding bytes, the salt length indicator, and the salt itself. The fourth step involves extracting the salt from the data block. The verifier checks that the padding bytes are correct. They should be zeros with specific bits set in the leftmost byte. The verifier then extracts the salt value from the end of the data block. Step 5 is reconstructing M'. The verifier hashes the original message to get M hash, just as the signer did. The verifier then forms M' by concatenating 8 0 bytes, M hash, and the recovered salt. This M' is then hashed to get H'. The final step is comparison. The verifier checks whether H', the hash computed from the reconstructed M', matches H, the hash recovered from the signature. If they match, and if all the padding and structure checks passed, then the signature is valid. The match proves that the signature was created by someone who knew both the message and the salt, and who possessed the private key to perform the RSA operation. Security properties of RSA-PSS. The security of RSA-PSS is one of its most important features and the primary reason it's recommended over older RSA signature schemes. Let's explore what makes RSA-PSS cryptographically secure and why it has such strong theoretical guarantees. The fundamental security property of RSA-PSS is existential unforgeability under chosen message attacks, often abbreviated as EUFCMA. This is a strong security notion that means an attacker cannot create a valid signature for any new message, even if they can trick you into signing many other messages of their choosing. This protection is crucial in real-world scenarios where an attacker might have some level of interaction with a legitimate signer. RSA-PSS achieves this security through its use of randomness via the salt. Because each signature incorporates a fresh random salt, an attacker cannot predict what a signature will look like before it is created. This randomness prevents attacks that work against deterministic signature schemes, where seeing many signatures can reveal patterns or relationships that help in forgery attempts. The scheme has a provable security reduction to the RSA problem in the random oracle model. What this means is that cryptographers have proven mathematically that if you could break RSA-PSS signatures, then you could also solve the underlying RSA problem of computing eth roots modulo n. Since the RSA problem is believed to be computationally infeasible with sufficiently large keys, this proof gives us confidence that RSA-PSS is secure. The random oracle model is a theoretical framework where hash functions are assumed to behave like truly random functions. While real hash functions aren't perfect random oracles, this model has proven to be a useful tool for analyzing cryptographic schemes, and schemes proven secure in the random oracle model generally hold up well in practice when instantiated with good hash functions like SHA-256 or SHA-512. Another important security aspect is resistance to signature forgery through algebraic manipulation. The encoding process in RSA-PSS, with its use of MGF1 and the specific way the salt and message hash are combined, makes it extremely difficult to manipulate signatures or combine multiple signatures to forge new ones. The mask generation function ensures that even knowing multiple valid message signature pairs does not help an attacker predict or construct signatures for new messages. Parameter selection for RSA-PSS. Choosing the right parameters for RSA-PSS is crucial for both security and compatibility. Let's discuss the key parameters you need to select and the considerations for each one. The first and most important parameter is the RSA modulus size, denoted as N in bits. For RSA-PSS, as with all RSA cryptography, the security level depends heavily on this modulus size. Current recommendations from NIST and other standards bodies suggest a minimum of 2048 bits for RSA moduli, which provides approximately 112 bits of security. For higher security levels, 3072-bit moduli provide approximately 128 bits of security, and 4096-bit moduli provide even stronger protection. The choice of modulus size has practical implications that extend beyond just security. Larger moduli, for example, led to slower signature generation and verification operations, and they also result in larger signature sizes. For instance, a 2048-bit RSA key produces 256-byte signatures, whereas a 4096-bit key produces 512-byte signatures. Therefore, you need to carefully balance your security requirements against performance and bandwidth constraints within your specific application. The second critical parameter is the hash function. RSA-PSS supports various hash functions, but the most common choices today are SHA-256, SHA-384, and SHA-512 from the SHA-2 family. The hash function should be chosen to match your security level. For example, there is no point using a 2048-bit RSA key with SHA-1, which is now considered broken. Typically, SHA-256 pairs well with 2048-bit or 3072-bit RSA keys, while SHA-384 or SHA-512 might be used with 4096-bit keys for very high security applications. The salt length is another important parameter. The typical recommendation is to make the salt length equal to the hash output length. So with SHA-256, you would use a 32-byte salt. However, the PSS specification allows for flexibility here. You can use shorter salts if you are constrained by signature size, though this slightly reduces security. The minimum salt length should be at least 20 bytes, even with shorter hash functions. Some implementations default to zero-length salts for compatibility reasons, but this eliminates the randomness that makes PSS superior to deterministic schemes. The mask generation function parameter is typically MGF1, and within MGF1, you specify which hash function to use for the masking operation. Usually, this is the same hash function used elsewhere in the PSS process, but technically it could be different. In practice, everyone uses the same hash function throughout for simplicity and to avoid potential security issues from mixing different hash functions. RSA-PSS in practice. Open Secure Sockets Layer examples. Let us look at how to actually use RSA-PSS in practice with OpenSSL, which is one of the most widely used cryptographic libraries. OpenSSL provides comprehensive support for RSA-PSS through its command line tools and programming APIs. First, let's generate an RSA key pair suitable for use with PSS. You use the OpenSSL genpkey command with the RSA algorithm. The pkey-opt flag allows you to specify the RSA modulus size. Here we're using 2048 bits. The out flag specifies where to save the private key file. This command generates a private key that can be used for PSS signatures. The key itself isn't PSS specific. RSA-PSS uses standard RSA keys, but applies them with the PSS padding scheme. To extract the public key from the private key, you use the Open Secure Sockets Layer pkey command. The in flag specifies your private key file. The pub out flag indicates you want the public key output, and out specifies where to save it. Now you have a key pair ready for signing and verification operations. To sign a file using RSA-PSS, you use the Open SSL digest command in a specific way. The SHA-256 flag specifies the hash function. You could also use SHA-384 or SHA-512, depending on your security requirements. The SIG-opt flag is crucial. This is where you specify RSA-PSS parameters. The RSA padding mode PSS setting tells OpenSSL to use PSS padding instead of the default PKCS version 1.5 padding. You can also specify the salt length using RSA-PSS salt length. Setting it to digest means the salt length matches the hash output length, which is the recommended configuration. The sign flag indicates you are creating a signature rather than verifying one, and InKey specifies your private key file. The out flag tells OpenSSL where to save the signature, and finally you specify the file you want to sign. OpenSSL will read the file, hash it with SHA-256, generate a random salt, perform the PSS encoding, and create the signature using your private key. Verification is similar but uses different flags. You still specify the hash function and PSS parameters the same way. Instead of the sign flag, you use verify with the public key file. You also specify the signature file with SIG file and the original file you want to verify. OpenSSL will perform the verification process we discussed earlier, and it will output whether the signature is valid or not. In programming contexts using the OpenSSL library, you have more fine-grained control over all the PSS parameters. You can specify exact salt lengths, control the MGF1 hash function separately, and handle the signature operations in memory rather than with files. The CAPI provides EVPPKEY functions for signing and verification, along with EVPPKEYCTX functions for setting up the PSS parameters. Most modern programming languages have bindings to OpenSSL or similar cryptographic libraries that expose RSA-PSS functionality. RSA-PSS in TLS 1.3. Transport Layer Security version 1.3, the most recent version of the protocol that secures HTTPS connections, has made RSA-PSS a mandatory signature algorithm. This represents a significant shift in how the Internet handles digital signatures and reflects the cryptographic community's confidence in PSS's security properties. In TLS 1.3, when a server authenticates itself to a client, it can use RSA-PSS to sign the handshake transcript. The handshake transcript is a hash of all the messages exchanged during the TLS handshake up to that point. By signing this transcript with RSA-PSS, the server proves it possesses the private key corresponding to its certificate's public key, and it binds this proof to the specific handshake session. The randomness in PSS ensures that even if the same server performs many handshakes, each signature is unique. TLS 1.3 specifically defines signature algorithm identifiers for RSA-PSS with different hash functions. For example, RSA-PSS RSA-ESHA-256 indicates RSA-PSS using SHA-256, where the signature is generated with a key that came from an RSA certificate. There is also RSA-PSS PSS SHA-256, which indicates the certificate itself uses PSS rather than traditional RSA. The distinction is important for certificate chain validation. The protocol requires that when RSA-PSS is used in TLS 1.3, the salt length must equal the hash output length. So for SHA-256, you must use a 32-byte salt. This standardization ensures interoperability between different TLS implementations. The MGF1 function within PSS must also use the same hash function as the main signature hash. These requirements remove ambiguity and ensure that all implementations handle PSS signatures consistently. One interesting aspect of TLS 1.3's adoption of RSA-PSS is that it has driven implementation improvements across the ecosystem. Many cryptographic libraries that previously had incomplete or buggy PSS implementations were forced to fix these issues to support TLS 1.3. This has had the beneficial side effect of making RSA-PSS more robust and reliable even for non-TLS applications. Certificate authorities and RSA-PSS. The world of X.509 certificates and certificate authorities is gradually transitioning to RSA-PSS for certificate signatures. When a certificate authority issues a certificate, it signs the certificate using its own private key. Historically, this signature used the older PKCS1 version 1.5 padding scheme. Modern CAs are now issuing certificates signed with RSA-PSS, and this transition has important implications. A certificate signed with RSA-PSS includes additional parameters in the signature algorithm identifier field. These parameters specify the hash function, the MGF1 hash function, the salt length, and the trailer field value. This is different from traditional RSA signatures where these parameters were often implicit or had fixed values. The explicit parameter encoding ensures that verifiers know exactly how to verify the signature without ambiguity. The CA/Browser Forum, which sets standards for publicly trusted certificate authorities, has been updating its baseline requirements to accommodate RSA-PSS. CAs must ensure their root and intermediate certificates can handle PSS signatures in the chain. This means if a CA wants to issue end entity certificates signed with RSA-PSS, its intermediate CA certificate must also support PSS, either by being signed with PSS itself or by having a public key that can verify PSS signatures. One complexity that has emerged is the distinction between RSA keys in traditional PKCS number 1 certificates versus keys specifically designated for PSS. Some certificates now include an explicit indication that the public key should only be used for PSS signature verification, not for traditional RSA signatures. This is encoded in the subject public key info field with a specific algorithm identifier. This distinction helps prevent confusion and ensures keys are used only for their intended purpose. For organizations deploying RSA-PSS certificates, compatibility is a key concern. Older TLS implementations that do not understand PSS will fail to validate PSS signed certificates. This has led to a careful, gradual rollout where CAs often maintain dual certificate chains. One signed with traditional RSA for compatibility, and one signed with PSS for modern clients. Load balancers and servers can select which chain to present based on the client's advertised capabilities during the TLS handshake. Common implementation pitfalls. Implementing RSA-PSS correctly requires attention to several subtle details, and getting these wrong can lead to security vulnerabilities or interoperability problems. Let us examine the most common mistakes and how to avoid them. The first major pitfall is salt reuse. Remember, the security of RSA-PSS relies on using a fresh, random salt for each signature. If you reuse salts, or, worse still, use a constant salt or a zero-length salt, you lose the security advantages of PSS and essentially have a deterministic signature scheme. Some implementations default to zero-length salts for performance or compatibility reasons, which is cryptographically weak. Always configure your implementation to use random salts equal to the hash output length. The second pitfall involves parameter mismatches between signing and verification. If you sign with SHA-256 but try to verify with SHA-512, the verification will fail. Similarly, if the salt length used during verification does not match what was used during signing, verification will fail. Some implementations allow automatic salt length detection, while others require explicit configuration. When building systems, document which parameters you are using and ensure both signers and verifiers use matching parameters. A third common error is incorrect MGF1 implementation. The mask generation function has specific requirements about how the counter is encoded and concatenated with the seed. The counter must be a 4-byte big Indian integer. Some implementations have gotten this wrong, encoding the counter in Little Indian format or using fewer than 4 bytes. This breaks interoperability because the masks generated during signing will not match those generated during verification by a correct implementation. Buffer overflow and padding validation errors are another source of problems. When parsing an encoded message during verification, implementations must carefully check that all padding bytes are correct, that the masked database has the right structure, and that indices don't go out of bounds. Failing to validate these properly can lead to vulnerabilities where an attacker provides malformed signatures that might crash the verifier or, even worse, trick it into accepting invalid ones. Timing side channels are a subtle but serious concern. If the verification process takes different amounts of time, depending on where a signature fails validation, an attacker who can measure these timing differences might learn information about the signature, or even the private key. Constant time implementations that always perform the same operations regardless of intermediate results are necessary for high-security applications. This is particularly important when verifying signatures in scenarios where an attacker can submit many signatures and measure response times. Performance characteristics. Understanding the performance characteristics of RSA-PSS is important for capacity planning and architectural decisions. Let's examine what affects RSA-PSS performance and how it compares to alternatives. The dominant factor in RSA-PSS performance is the RSA modular exponentiation operation. When signing, you compute m to the power of d modulo n, where d is your private exponent. When verifying, you compute s to the power of e modulo n, where e is the public exponent. These operations involve very large numbers. A 2048-bit RSA key means working with numbers that are 617 decimal digits long. The computational complexity grows significantly with key size. Signature generation is considerably slower than verification. This asymmetry exists because the private exponent d is typically much larger than the public exponent e. The public exponent is often chosen to be a small value, which has only 2 bits set and allows for optimization. This means verification can be done very quickly using a technique called exponentiation by squaring. However, the private exponent is necessarily large and random, so signing operations take much longer. To give you concrete numbers, on a modern server CPU, signing with a 2048-bit RSA-PSS key might take around 1 to 2 milliseconds per signature. Verification with the same key might take around 50 to 100 microseconds. These numbers vary based on the CPU, the quality of the implementation, and whether hardware acceleration is available. With a 4096-bit key, signing might take 8 to 10 milliseconds, while verification takes 200 to 300 microseconds. The performance scales roughly as the cube of the key size. The PSS encoding and decoding operations themselves add minimal overhead compared to the RSA operation. The hash functions and MGF1 are fast, computing SHA-256 on typical message sizes and generating masks adds perhaps a few microseconds to the total time. The XOR operations for masking are essentially free. This means PSS overhead compared to traditional PKCS 1.5 RSA signatures is negligible. Any performance difference is in the noise. Hardware acceleration can dramatically improve performance. Many modern CPS include instructions for large integer arithmetic, and some include specific acceleration for RSA operations. Hardware security modules, or HSMIS, can perform RSA operations much faster than software, sometimes achieving thousands of signatures per second. GPS can also be used for parallel RSA operations when you need to generate or verify many signatures simultaneously. For high-throughput applications like certificate authorities or secure messaging systems, hardware acceleration is often essential. RSA-PSS versus ECDSA. When choosing a signature algorithm for your application, the two main contenders today are RSA-PSS and ECDSA, which stands for Elliptic Curve Digital Signature Algorithm. Let's compare these two to understand when you might choose one over the other. The fundamental difference is the mathematical problem they are based on. RSA-PSS security relies on the difficulty of factoring large composite numbers. ECDSA security relies on the difficulty of the elliptic curve discrete logarithm problem. Both problems are believed to be computationally hard, but they have different characteristics. The discrete logarithm problem on elliptic curves appears to be harder for a given key size, which means ECDSA can use much smaller keys. Key size is where ECDSA has a major advantage. A 256-bit ECDSA key provides roughly equivalent security to a 3072-bit RSA key. This means ECDSA keys are about 12 times smaller. The signatures are also smaller. An ECDSA signature is about 64 bytes for the P256 curve, while an RSA-PSS signature is 256 bytes for a 2048-bit key, or 384 bytes for a 3072-bit key. For applications where bandwidth is limited, or where you are storing many signatures, this size advantage is significant. Performance comparisons are more nuanced. ECDSA signature generation is generally faster than RSA-PSS, because the elliptic curve operations work with smaller numbers. However, ECDSA verification is slower than RSA-PSS verification. This is because RSA can use a small public exponent for fast verification, while ECDSA verification requires a full elliptic curve point multiplication. So, if your application generates signatures rarely but verifies them frequently, RSA-PSS might perform better. If you generate signatures often, ECDSA might be faster. From a security perspective, both are considered secure when appropriate parameters are used. RSA-PSS has the advantage of being around longer and being more thoroughly analyzed. The security proof for PSS is well established. ECDSA also has strong security properties. However, more implementation vulnerabilities have been discovered in ECDSA, often related to random number generation. ECDSA requires a fresh, random nonce for each signature. If you ever reuse a nonce or use a predictable one, the private key can be recovered. RSA-PSS is more forgiving. A weak salt reduces security but does not immediately expose the private key. Compatibility and standardization favor RSA-PSS in some contexts. RSA has been around since the 1970s and is universally supported. Every cryptographic library and hardware security module supports RSA. ECDSA is newer, and while widely supported now, you might encounter older systems that do not support it. However, for new systems and protocols, ECDSA is increasingly preferred because of its efficiency. TLS 1.3, for example, supports both but encourages ECDSA. The choice often comes down to your specific requirements regarding compatibility, performance, key size, and implementation maturity. RSA-PSS versus EDDSA. EDDSA, which stands for Edwards Curve Digital Signature Algorithm, represents the latest generation of signature schemes. Specifically, ED 25519 using the curve 25519 elliptic curve has gained significant popularity. Let us compare RSA-PSS with EDDSA to understand where each one fits. EDDSA was designed from the ground up with security and simplicity in mind. Unlike ECDSA, which has multiple parameters and curve choices that can be configured incorrectly, EDDSA specifies everything precisely. ED uses a specific elliptic curve, a specific hash function, and a specific signature format. This rigidity is actually a strength because it eliminates entire classes of implementation errors. There's no way to misconfigure the parameters because there are no parameters to configure. Performance-wise, EDDSA is extremely fast. ED 25519 can generate thousands of signatures per second on a single CPU core, and verification is equally fast. Both operations are faster than RSA-PSS, and significantly faster than ECDSA. The reason is that Curve 25519 was specifically designed for fast implementation. The curve arithmetic uses efficient formulas, and the coordinate system is chosen to avoid expensive operations. Additionally, EDDSA signatures are deterministic, which means no random number generation is needed during signing. The determinism of EDDSA might seem like a disadvantage compared to PSS's randomness, but EDDSA achieves security through a different approach. Instead of using an external random number, EDDSA derives a deterministic nonce from the private key and message using a hash function. This nonce is unique for each message but does not require randomness. This eliminates random number generation as a potential point of failure. The security proof for EDDSA is strong and does not rely on random oracles like PSS does. Key and signature sizes for EDDSA are excellent. An ED 25519 public key is 32 bytes, a private key is 32 bytes, and a signature is 64 bytes. Compare this to RSA-PSS where a 2048-bit public key is 256 bytes, the signature is 256 bytes, and the private key is larger still. For applications where size matters, such as embedded systems, blockchain applications, or protocols with tight packet size constraints, EDDSA's compact sizes are very attractive. The main advantage RSA-PSS retains over EDDSA is maturity and standardization. RSA has decades of deployment experience, while EDDSA is relatively new. Some compliance frameworks or security certifications specifically require RSA, and changing these requirements takes time. Additionally, some hardware security modules have excellent RSA acceleration but don't yet support EDDSA. However, for new systems without legacy constraints, EDDSA is increasingly the recommended choice because it's faster, smaller, and has a cleaner design that's harder to implement incorrectly. Migration from PKCS number 1 version 1.5 to PSS. If you have an existing system using traditional PKCS number 1, version 1.5 RSA signatures, and want to migrate to RSA-PSS, you need to plan carefully to maintain compatibility and security throughout the transition. Let's discuss strategies for successful migration. The first consideration is backwards compatibility. Systems verifying signatures need to be updated before systems generating signatures. If you start generating PSS signatures before your verifiers understand PSS, those signatures will be rejected. The typical migration path is to first deploy verifier updates that can handle both traditional and PSS signatures. These verifiers check which signature scheme was used and apply the appropriate verification algorithm. Once all verifiers are updated, you can start rolling out signer updates that generate PSS signatures. During the transition period, you might need to support dual signatures or signature algorithm negotiation. For example, a client might advertise which signature algorithms it supports, and the server selects an appropriate one from the intersection of what the client supports and what the server prefers. This is how TLS handles the transition. Clients list supported signature algorithms in the handshake, and servers pick the strongest one they support from that list. Certificate chains require special attention during migration. If you're using PSS for certificate signatures, remember that intermediate CA certificates must also support PSS. You can't have a PSS signed end entity certificate chained to an intermediate that only has a traditional RSA public key. You might need to issue new intermediate certificates specifically for PSS, or use cross certificates where the same intermediate is signed both ways. Once with traditional RSA for legacy clients and once with PSS for modern clients. Testing is crucial during migration. You need to test that your PSS implementation correctly signs and verifies messages. Test with multiple message sizes, including empty messages. Test with different salt lengths. Test interoperability with other implementations. Sign with your library and verify with OpenSSL, and vice versa. Test error cases. What happens when you try to verify an invalid signature, or a signature with wrong parameters, or a signature for a different message? Comprehensive testing catches implementation bugs before they cause production problems. Documentation and configuration management are important too. Make sure your operations team understands which systems use which signature algorithms. Document the parameters you have chosen, such as the hash function, salt length, and key sizes. Have a rollback plan in case you discover problems during the migration. Consider using feature flags or gradual rollouts where you start by using PSS for a small percentage of signatures and gradually increase as confidence grows. Monitor error rates and validation failures during the transition to catch issues quickly. RSA-PSS in modern protocols. Beyond TLS, RSA-PSS has been adopted by numerous modern protocols and standards. Understanding where PSS fits in the broader cryptographic ecosystem helps inform design decisions for new systems. In the JSON Web Signature Standard, known as JWS and defined in RFC 7515, RSA-PSS is supported through specific algorithm identifiers. PS256 indicates RSA-PSS with SHA-256. PS384 uses SHA-384, and PS512 uses SHA-512. These JWS algorithms are used extensively in modern web authentication systems. JSON Web Tokens, or JWTs, can be signed with PSS, providing strong authentication for API requests, single sign-on systems, and OAuth 2.0 flows. The compact encoding of JWTs makes them suitable for HTTP headers, and PSS provides the signature security. The JOSE framework, which stands for JavaScript Object Signing and Encryption, builds on JWS and includes RSA-PSS as a preferred algorithm. JOSE is used by many cloud services and identity providers. When you authenticate to a cloud API using a service account key, that authentication often involves a JWT signed with RSA-PSS. The widespread adoption of JOSE has made PSS implementations more mature and better tested because any bugs would affect major internet services. In the email security world, SMIME and PGP are gradually adding PSS support. SMIME version 4 includes specifications for using RSA-PSS for email signatures. This allows email clients to sign messages with PSS, providing stronger security guarantees than the traditional RSA signatures. However, adoption has been slow because of the huge installed base of email clients and the need for backwards compatibility with clients that do not understand PSS. Document signing formats, like PDF signatures, are also incorporating RSA-PSS. The PDF specification allows for various signature algorithms, and recent versions explicitly support PSS. This is important for legal and regulatory contexts where digitally signed PDFs serve as binding contracts or official records. The provable security of PSS gives confidence that these signatures will remain secure for the lifetime of the documents, which might be decades. Blockchain and cryptocurrency systems have diverse signature algorithm choices, but some use RSA-PSS while most blockchains prefer elliptic curve signatures because of their smaller size. Certain applications that need RSA compatibility or have specific regulatory requirements use PSS. Smart contract platforms that support multiple signature algorithms often include PSS as an option, allowing developers to choose based on their specific security and performance requirements. Advanced topics and research. The field of digital signatures continues to evolve, and RSA-PSS remains an active area of research. Let's explore some advanced topics and recent developments in PSS cryptography. One area of ongoing research is post-quantum cryptography. Quantum computers, when they become practical, will be able to break RSA using Shor's algorithm. This algorithm can factor large numbers efficiently on a quantum computer, which would completely break RSA's security, including RSA-PSS. The cryptographic community is developing post-quantum signature schemes that will resist quantum attacks. However, these new schemes are still maturing, and RSA-PSS will remain important during the transition period and in contexts where quantum computers aren't a threat. Threshold signatures are an interesting extension of RSA-PSS in a threshold scheme. The private key is split among multiple parties, and a minimum number of them must cooperate to generate a signature. This is useful for high-security applications where you don't want any single entity to have complete signing authority. Threshold RSA-PSS is more complex than threshold ECDSA because of how RSA keys work, but it's possible and has applications in distributed systems and multi-party computation. Blind signatures are another advanced cryptographic primitive that can be built with RSA in a blind signature scheme. Someone can get a signature on a message without revealing the message to the signer. This has applications in privacy-preserving protocols like anonymous credentials or digital cash. While traditional RSA supports blind signatures, extending this to PSS requires careful analysis because the randomness in PSS interacts with the blinding process in subtle ways. Researchers have developed protocols for RSA-PSS blind signatures, but they are more complex than the traditional RSA blind signature schemes. Side-channel analysis remains an important research area. Even though PSS is mathematically secure, implementations might leak information through timing, power consumption, electromagnetic emanations, or other physical channels. Researchers continue to discover new side-channel attacks and develop countermeasures. Constant time implementations, masking techniques, and hardware protections are all part of defending against these attacks. For high-security applications, using certified hardware security modules that resist side-channel attacks is important. Formal verification of PSS implementations is gaining attention. Using mathematical proof techniques and automated tools, researchers can verify that a specific implementation of RSA-PSS correctly follows the specification and doesn't have security bugs. Projects like Project Everest have formally verified cryptographic implementations including signature schemes. As formal verification tools become more practical, we may see formally verified PSS implementations becoming standard in high-assurance systems. Conclusion and best practices. As we conclude our exploration of RSA-PSS, let's summarize the key takeaways and best practices for using this signature scheme effectively and securely. RSA-PSS represents the state-of-the-art for RSA-based digital signatures. Its provable security properties, standardization in modern protocols like TLS 1.3, and widespread implementation support make it the clear choice for any new system that needs RSA signatures. The days of using PKCS number 1 version 1.5 should be behind us. PSS provides better security with minimal performance overhead. When implementing or configuring RSA-PSS, follow these best practices. First, use a random salt equal in length to your hash output for each signature. Never reuse salts, and avoid zero-length salts unless you have a compelling compatibility reason. Second, match your hash function to your security level. Use SHA-256 for 2048-bit keys, and SHA-384 or SHA-512 for larger keys. Third, use sufficiently large RSA keys. A minimum of 2048 bits is recommended, or 3072 bits or more for higher security. Fourth, ensure your implementation properly validates all padding and structure during verification to avoid vulnerabilities. From an architectural perspective, consider the full system context. Think about performance requirements. Can your system afford RSA's computational cost? Or should you consider elliptic curve alternatives like ECDSA or EDDSA? Consider compatibility. Do you need to interoperate with legacy systems that might not support PSS? Consider key management. How will you generate, store, and rotate RSA keys securely? For critical systems, consider using hardware security modules to protect private keys and accelerate signature operations. Stay informed about cryptographic best practices and standards. The field evolves as new attacks are discovered and new techniques developed. Subscribe to security advisories for the cryptographic libraries you use. Update your systems regularly to get security fixes and improvements. Participate in security reviews and audits to catch implementation problems before attackers do. Looking forward, while RSA-PSS will eventually be superseded by post-quantum signature schemes, it will remain relevant for many years. The installed base of RSA infrastructure is enormous, and migration to new cryptographic primitives takes time. RSA-PSS provides a solid foundation for secure digital signatures in the medium term, balancing proven security, broad compatibility, and practical performance. Thank you for your attendance. Please consider subscribing to the channel.